In the third unit of this lecture, we're going to now more formally introduce multi-layer perceptrons. Multi-layer perceptrons are feed-forward neural networks. And feed-forward here means that they're structured in layers and there's no feedback connections between layers. Each layer only feeds forward information to the next layers, starting from the input all the way to the output layer. And they compose several nonlinear functions. Functions, as we've seen before, affine plus logistic. So here you can see an example. We can consider a function f of an input x that is decomposed as a function of hidden layers. So first x is input to h1, and then the output is input to h2, and that output is input into h3, and that output is then input into y hat. So the last layer, the output layer that predicts the final prediction. And so all the layers that are not the output layer, that don't receive direct supervision, that don't receive direct the training label, the training signal, are called hidden layers because they are not directly observed. They are layers that in intermediate stages of the neural network try to learn useful feature representations for the output layer to predict or classify correctly. The data only specifies the behavior of the output layer. That's where this name hidden comes from. And each of these layers, here I is one layer, 1, 2, 3, comprises multiple neurons, J, which are implemented as affine transformations followed by some nonlinear activation function. That could be, for instance, a sigmoid activation function that we've seen already, but we have a whole variety of activation functions that we can use at our disposal today, and we'll see some of them. So here's the generic expression, right? In contrast to what we've seen before is that in this case here now we have multiple neurons, multiple units. They're called neurons because of their neuroscientific motivation. But really they're just these affine plus nonlinear activation function expressions. We have for each layer I, we have multiple neurons J. And as such, we have also multiple times to do this transformation. Of course, we can do this again using matrix and tensor operations to stack them into bigger matrix tensor operations that are efficient to compute. Each neuron in each layer, and that's specific to multi-layer perceptrons, is fully connected to all neurons of the previous layers. This is where the structure of these layers becomes apparent, and we'll see that on the next slide. We'll see that there's multiple layers, and there is no connections of neurons within a layer, but there's connections of neurons between layers, and in particular between adjacent layers. All neurons are fully connected. This is a matter of the architecture, and the multi-layer perceptron is a specific architecture. There's many more architectures that have been developed and that are used today, but this is just one of the most basic ones. And the overall length of the chain of this computation of the model is the depth of the model. It's called the depth of the model. And that's where the terminology deep learning comes from. We are stacking many of these hidden layers on top of each other or behind each other. So we get a deeper and deeper model. And we'll see the relevance of this depth with respect to what's called the width of the model in the last part of this lecture. However, I personally find the name multi-layer perceptron a bit misleading, as it's used for modern neural networks that are trained with backpropagation and that have differentiable nonlinear activation functions that are continuous. And this is in contrast to these threshold units that are not differentiable, and they were used in the perceptron algorithm. So that's why I think it's a little bit misleading to call these perceptrons, because actually neither the perceptron algorithm is used to train them. We train them with backpropagation, nor the linear threshold unit is used, but instead we use an affine plus a differentiable activation function. So it's kind of a smooth approximation of the threshold unit. So what does a multi-layer perceptron look like? So this is an example of a multi-layer perceptron network architecture. You can see here the inputs on the left. This is the input layer. Then we have 3 hidden layers, and then we have the output layer. And the variables within a layer are not connected, but the variables within a layer, the variables of one layer are fully connected to all the variables of the previous layer. So for instance, this variable here is connected to all 3 variables of the previous layer. In my notation here, I'm using the first index of the hidden layer variable, or the neuron in a hidden layer, as the layer index, and the second one as the neuron index within a layer. The depth of a neural network is specified as all computation layers. So we ignore the input layer, but we have just the number of computation layers. In this case, we have a network of depth 4. So we have 1, 2, and 3 hidden layers plus an output layer. In the case of a logistic regression model, we would just have 1 computational layer. So that would be a network of depth 1. The simplest multi-layer perceptron, or the first model that we could actually call deep, is a model with 2 layers that has 1 hidden layer and 1 output layer. In this particular case, we have an example of 4 computation layers. So the depth is 4. The width of a layer is specified as the number of neurons in a layer. So here in this layer, we have 3 neurons. Here we have 2 neurons. And here we have 3 neurons again. And so this network depth and the network width are central characteristics and design parameters of multi-layer perceptrons, because we can choose them freely depending on the application that we're considering. If we have very little data and a simple classification problem, we of course use less parameters, smaller networks, in order to not overfit, etc. So neurons are grouped into layers. Each neuron is fully connected to all previous ones. And a hidden layer here in vector notation, right, so it's basically this h with just 1 index, the boldface h, indicates the value of all nodes in a layer concatenated, is simply a affine transformation of the previous layer. So for instance, this here is an affine transformation of the previous layer. This is the hi-1, followed by an activation function that's applied element-wise to the resulting vector. And the parameters in this case are h and b. And please note that in this specific visualization here, I'm omitting the parameter nodes because it would get too cluttered. But each of these red nodes actually has a little, you can think of each of these red nodes having a little parameter node attached to it, which is the A and the B for each of these nodes. Or you can also think about these nodes as one, collapsing it to one, and then having one parameter node, like the matrix A and the vector B associated with it. Just for clarity here, I don't show them. Here's exactly this collapsed notation, where instead of the one-dimensional nodes and neurons, here we have combined them into vectors. So we have a vector-valued input and vector-valued hidden layers and a vector-valued output. And this is again a slide about the perspective I've already presented previously when introducing these models, which is about a layered computation that changes the representation So here we have a specific input representation. So for instance, the data set is embedded in this two-dimensional space here. And by passing these data points through these nonlinear layers, we're changing the representation. So for instance, if at the last hidden layer, we call the representation psi, so that we have now psi of x, this last hidden layer. You think of it as computing psi of the input x. And if I draw this psi of x, in this case it's also a two-dimensional example, so we're transforming from 2D to 2D, then the goal of representation learning is to learn a useful representation at the last hidden layer, such that this output layer, which is effectively just a logistic regressor in the classification case, right? It's exactly, each of these individual errors here is just a logistic regressor. So the last one is also a logistic regressor, which means that it can only linearly distinguish data points. So what this first layer should do is we should transform the data in a way that it becomes linearly separable. And this is illustrated here. So, in an ideal situation, we would transform all these data points here through these layers such that in this hidden layer 3, we get a representation that is linearly separable, and where the class 0 and the class 1 can simply be separated by this final linear logistic output head. And here you see an exemplary decision boundary in red. So this is the perspective I'd like to give you on how to think about these models and why it's called representation learning, because really what we learn here is a transformation of representations. So with each layer we should learn a better representation such that it becomes more, the data points become more easy to classify, become more separated with each layer. Here's a couple of examples of activation functions that we can use. We have already seen the sigmoid activation functions, but there's other activation functions that people use. The sigmoid is inspired by neuroscience, but it turns out that it's not ideal because it has it very quickly saturates, and then once it's saturated, the gradients are very small, and if the gradients are small, it means the network doesn't learn anything anymore, because the gradient descent-based optimization algorithm doesn't update anymore because the gradients are 0. So one very popular function that's used these days is the ReLU, or the leaky ReLU. ReLU stands for rectified linear unit, where we have, simply a max operator between 0 and x. So we clamp this linear function here at 0. So we have a nonlinearity. It's not even differentiable. Turns out it doesn't need to be differentiable. We can train neural networks also with non-differentiable functions. But the important thing is that the gradient, no matter like how far I go along the x coordinate, is always there. There's always a gradient here. In this case, actually, there's even a gradient everywhere. And this is a very useful property. And it turns out that it helps in learning models more efficiently and faster, despite deviating from the neuroscientific example. Now, this is just a teaser for the next lectures. We're going to go into these activation functions into more detail. So coming to the neural motivation, actually, the reason why these units are called neurons and the networks are called neural networks is that they are inspired by the brain. Neurons in the brain are also structured in layers, similarly to MLPs being structured in layers. And these neurons in the brain, they receive input from many other units and compute their own activation function. And the sigmoid activation function is guided by neuroscientific observations of how these functions actually behave. Now, of course, we don't have continuous functions in the brain. Rather, we have electric signals, impulses that are sent. So there's an example here. But the rate of signals and the rate of impulses can be modeled with such functions. So here's an example where we have a single neuron. The dendrites receive incoming electric signals through the synapses, through the neurotransmitters. And then the signal is accumulated in the cell and is, this is basically the linear combination. You can think of this as the linear combination in a logistic regression model. And then we have an axon that transports this information to another a little bit further away region in the brain, where then at this terminal axon head here, the information is then passed on through the neurotransmitters to through the synapses to dendrites of other cells. So there could be multiple other cells here that receive from this neuron here, and so the axon here determines basically the weight or the strength with which this information is transmitted. And this is how these neural networks in the brain relate to the artificial neural networks, very loosely speaking. Of course, at the physical level, they operate quite differently. And furthermore, the architecture and the training of modern neural networks differs radically. In this course, our main goal is not to model the brain. This is really important. Our main goal is instead to achieve statistical generalization. We want to have models that perform well. We are inspired by the brain, but we don't want to replicate the brain. We want to rather develop models that work well, that generalize well, that work well with little data, etc. And this is where neuroscience deviates from deep learning. Okay, so now how can we train an MLP? We have seen training algorithms before. Again, here we are going to use gradient descent, or what's called stochastic gradient descent. Stochastic gradient descent is a version of gradient descent where we are going to pick mini batches instead of the entire data set for computing gradients. Because if we have a very large data set, let's say ImageNet with millions of data points, it's very inefficient to compute the gradient with respect to each data point because we need to compute millions of gradients. This doesn't work in parallel anymore on the CPU or on the GPU. So we need to do it sequentially. Instead, what we do here is we compute the gradient only over a smaller subset of the data set, which is then effectively an approximation to the true gradient. It's a noisy approximation to the true gradient, but it still contains useful information. And due to the stochasticity, we also have some useful properties of sometimes being able to jump over local minima. So it's actually quite useful to have some stochastic process inside the gradient descent operation. Yeah, we'll talk more about optimization algorithms, but the very basic version of such a gradient descent or stochastic gradient descent algorithm goes as follows. So we initialize the weights, for instance, randomly. We pick a learning rate and then a mini batch size. This is the size of the data points we want to process in parallel. This is typically the size of data points that fit at the same time into the GPU memory, and they can be at the same time forward and backward propagated in the context of the backpropagation algorithm. So let's say we have a data set of 10,000 examples, but there's only 100 examples that fit into memory. So we pick a mini batch, a random mini batch of 100 examples every time in every iteration of the algorithm. And then we first draw this random mini batch. So we draw these 100 examples randomly from the data set. You could also do it sequentially, but theoretically it's more correct to draw them randomly. And then for all elements of this mini batch, let's say we have a mini batch of size 100, then for all 100 data points, we do, if we have a GPU, we do that in parallel. We forward propagate X through the network to calculate the intermediate values and also the output layer. So these are the H1, H2 hidden layers and the output layer Y hat. And then we backpropagate gradients through the network to obtain the gradient of the loss function with respect to all the parameters that we're interested in. These are all these A's and B's that are sitting inside these little nodes in the MLP that we've seen before. So we do this for all elements in the mini batch. And then we update the gradient with we go one step into the negative direction of the average. This is the average gradient over the mini-match. And that's basically it. It's very simple. If the validation error decreases, we have again a training and a validation set. So if the validation error continues to decrease, we go to step 2, otherwise we stop because we are starting to overfit again. Some remarks. Large data sets typically do not fit into GPU memory. That's why we typically for large data sets have a batch size that's smaller than the dataset size. For instance, 100 compared to 10,000 data points in total. Now, the examples that we'll show on the next slides are actually quite small with just few data points. So we can choose the mini batch size as the dataset size. So it's actually not a mini batch, but in every iteration, we are just computing the gradients, the average gradient over the entire dataset. So here's some notes on levels of abstraction. You've already seen that we need to think, when we design these networks, we need to think at multiple levels of abstractions simultaneously. So we need to think about the optimization algorithm. We need to think about the network structure of the layers, the size and width of the layers. We need to think about how to efficiently implement our operations using vectorized operations and about the arithmetic operations themselves. And it's really key to becoming a good engineer in machine learning, or in particular in deep learning, that you're able to simultaneously think about these multiple levels of abstraction. And it's not only key for deep learning, but in general as a researcher, is key to be able to simultaneously think about multiple levels of abstraction in order to make new discoveries. Here's a famous quote from Donald E. Knuth, who said, not in the context of deep learning, but in the context of programming in this case, the psychological profiling of a programmer is mostly the ability to shift levels of abstraction from low level to high level, to see something in the small and to see something in the large. So that's really key, not only for deep learning, but in particular for deep learning. Okay, so now let's look at our XOR problem again, and let's finally solve it. Here I've utilized this fantastic demo from Andre Carpati that's still online on this web link that you see below. And I encourage you to have a look yourself at this demo. So in this demo, you can live in your browser train a neural network, specify the neural network in such a textual interface. In this case, I've used a neural network that has in the first hidden layer has 2 neurons, and then it has 1 neuron in the output layer. And as an activation function, I use 10H instead of sigmoid because it has better convergence properties for these simple examples, these not normalized input examples that we have here. And as an output, I'm using a softmax that in this particular case corresponds actually to the sigmoid function. So this is really exactly the implementation of this XOR intuition that we've developed before, that can be represented by 2 logistic regressors, and then on top of these 2 results, 1 logistic regressor that does something. But in this case, we are not specifying that the first one should be an OR and an AND, and the second one should be an AND, but we're just randomly initializing the weights, and we let SGD, stochastic gradient descent, do its magic, and this is the result that it obtains. It depends a bit on the initialization. Actually, it turns out that it doesn't converge like super rapidly, but it converges to this, and you can see that it does what we expect. It basically separates the red from the green one, the green points in this case. Here's a more challenging problem with more data points that are less separable even than the previous ones. And you can see what the model does, this multi-layer perceptron does. It's again just a 1 hidden layer multi-layer perceptron, so it has just 2 layers, a hidden layer and an output layer. But what I'm changing here is the number of neurons in the hidden layer, and you can see how the complexity of the decision boundary changes if I'm increasing the number of neurons. And if I'm increasing it to 50 neurons, you can see that it's almost overfitting. So the number of neurons that is set, the architecture itself is a regularization parameter. It's an essential parameter of your architecture. You can regularize your networks using weight decay. We're going to talk about this by basically doing putting quadratic loss on the weights themselves, but you can also regularize by just reducing the number of neurons, for instance. So let's finally, to conclude this unit, talk quickly about expressiveness. This following two-layer MLP that we see here, this is exactly a two-layer MLP, as we've seen on the previous slides, can be written as in a single equation. Here we have just substituted this h into here. Right? This is this h. Now the question is, what would happen if we would be using a linear activation function instead of a nonlinear activation function? What do you think would happen if we would choose linear activation functions? Would, in this case, a deep neural network also be a better choice, a more expressive choice than a simple linear classifier that has just a single layer? And would more layers help, going beyond 2 layers, going towards 3 and 4 layers? Now the answer to this question is no. And the reason for this is that no matter what the depth of this multi-layer perceptron is, if I'm choosing the activation functions as linear, I can always recombine by multiplying in the matrices, the equations, such that I end up with a linear equation again. So here in this particular example for a 2-layer MLP, this is the equation that I obtain if I'm removing the G, because I'm assuming linearity of the activation. And then I can multiply in A2 here. So I'm getting this expression. And then what I see is, of course, this expression here is just a vector. So I can relabel that vector as B. And this matrix here is just another matrix which I can relabel as matrix A. So I didn't gain anything. I have just added redundancy, which is actually a bad thing, because if I would optimize this with a nonlinear optimizer, it would be harder to optimize with this redundancy and dependency between variables. But it turns out actually it's a linear problem, so it has a closed form solution, and we didn't gain anything in terms of expressiveness. So the bottom line here is really crucial that we have these nonlinearities interleaved between these affine transformations. Otherwise, we wouldn't gain anything in terms of expressiveness. Yeah, with linear activations, a multi-layer perceptron can only express linear functions. So what is the model capacity of MLPs with nonlinear activation functions actually? This is the more interesting questions, right? If we're having these nonlinear activation functions, so is it better to build deeper networks? Is it better to build wider networks? How deep do we need to go in order to express arbitrarily complex functions, for instance? This is what we're going to discuss in the next unit.